they have the skills to back it up. And then a healthy home is a home that's safe, right? We need to feel comfortable, safe in our home, protected, and has good indoor air quality. And manages moisture well, so we'll talk some about this. And doesn't have any toxic materials in a state that could be harmful. So what I mean here is that, oftentimes there's like asbestos duct wrap, tape on old ducts, but it's a harmful material. But if you seal it with mastic, for instance, then it's not a state that can be harmful. It's pest free. So pests, they can destroy your insulation. They can destroy a lot of things in a home. And so it's one of the things, thinking about home performance is how do we also make sure that we're not going to get pests in the house to destroy our investment. Good light. It's an obvious one, but makes a big difference. And then a comfortable home is our sanctuary. That goes along with feeling safe, right? Help us feel safe and protected. Allows us to focus on other things, it allows us to focus on things other than our basic needs, and should also have well-regulated temperatures. A comfortable home that has well-regulated temperatures, good insulation, and all of that, then you're not thinking about, oh, I'm hot, which I am right now, or I'm cold. You're just comfortable, right? And then you can, your home is supporting your activities. Should have good sound control and should be cozy. And a home which reflects the values of its owners, supports our own values, and encourages our individuality. So this is, an example of somebody who rented this ADU, and he rented it because of how the creative kind of person that he was, and he brought in his skull, and and it just really fit his personality. And celebrates our differences. Everybody's totally different, right? And so I've worked on a lot of different types of homes, and to me, it's not about me and what I want as a designer. It's about you, and celebrating that. Should also support our interests, so that's kind of a program thing. And it is a good neighbor. So you see some of the houses I've designed, they're not standing out saying, hey, look at me. It's not that I'm against contemporary design. I've done plenty of contemporary projects, but I believe that if they're done well in a way that is still a good neighbor, then contemporary is great. It fits. An environmentally responsible home obviously helps protect our natural resources, reduces our carbon footprint, reduces waste, is also more comfortable. So this is a kind of a side effect of having a high performance home, is that it's also just becomes a lot more comfortable because of there's a lot of reasons for it, which I don't necessarily go into, but or maybe we will here in a little bit. Is also safer. So we think about, construction or the combustion appliances. We look at asbestos in the home. We look, we test for radon. All of those things. We come in and we make sure that it's also going to be a safe home. And so in the end, it's a healthier environment. All right. Does anybody have any questions about any of that overall? So we'll dive kind of into home performance, which is, might be a big reason why you're here. Like I said, I did home performance pretty much full time for about 4 years. I learned a lot, still a big part of what I do. home performance is kind of a nice way to say, building science, building science for homes. And this is something that, for commercial buildings, we always would hire a building scientist to review our plans. There's all sorts of liability reasons, behind that and everything, but also just to make them better, And so I see no reason why we shouldn't be considering building science on homes. So this just kind of goes into some of the definitions for home performance. Home performance is a term used to describe how all aspects of a home work together as one comprehensive system. So you do one thing somewhere and it affects something else in the home. Another definition, home performance refers to comprehensive assessment and optimization of a home's functionality, efficiency, comfort, and safety. It involves evaluating improving various aspects of the home systems and structures to ensure that they work together effectively. And the interesting thing to me is, because I'm a designer, I might add some things to the definition of home performance, because to me, how we live in our homes is also a performance thing. So I might add things like healthy, durability, water management, security, livability, organization, serviceability, flexibility, expandability, and adaptability. So a lot of folks, especially as they age, they need to adapt to their homes in order to stay in them. And so considering that is an important consideration. So this is a home as a system. This is a diagram that we saw a lot, as I was learning about home performance. This shows all the different, systems in a house, the insulation, the orange, installation surrounding it, the mechanical system up in the attic, the washer and dryer, furnace, water heater, crawl space, all of these things. These are all the systems in a home. A home's quite complex, and there's a lot to understand about all these things and how they affect each other. Each one of these is a rabbit hole of things to learn. And then this is me in roughly 2008 or so doing a blower door test on a house. This is the building. This is the BPI certification that I got. But first, I want to talk a little bit about water, okay? Because water is a big deal, especially when you're talking about home performance. As I say here, water is an incredible critical resource that helps make life possible on Earth, right? We wouldn't be here without water. However, it's also a building's mortal enemy. So water is a science in itself, and there's a lot to understand and learn about water, how it acts, how it behaves, how it affects buildings. So a lot of what I did and still do to this day is also water mitigation type of stuff, drainage and flashing and gutters and all of this. And I find it really fascinating. It's just, I'm a bit of a science geek, so it clicks for me. I would say, it's probably the most important aspect of building science, because, what happens when we get water in our buildings and it doesn't dry out. Several entire industries to manage it, So first we must consider how our building and the site handles the water. This is one of the reasons why I'm a big proponent for simple designs. That when we get too complex with our roof lines and things like that, it makes it difficult to roof those. makes it difficult to flash them, and we're just inviting an opportunity for the water to, attack our home. So it's that's sort of a Murphy's Law thing, right? It's like, if you give it an opportunity to happen, it probably will happen. So first, I'll try not to get too geeky, okay? But there's some things that are really important to understand about, especially if you're interested in home performance. And that is this thing called drying potential. So you have a heat source here. A home that has no insulation, right, and water running down the face of it has dramatic energy transfer, right? All that heat that you're paying for going right through your walls, and it's taking water with it, okay? So that's the rate of evaporation is very high. So that's why I have this little diagram here showing the high rate of evaporation. So what happens when we insulate our homes? Now we've reduced the energy transfer through our building envelope, and we've drastically reduced the drying potential. Does that make sense? Okay, it's a really important concept. Okay, and then so what happens when you have low drying potential, right, and enough water? We get mold, we get fungus, dry rot, all these things that are breaking our house down, right? So water management systems such as the roof, the gutters, the flashing, the water resistant barrier, the WRB we call this, or the Tyvek, and all of that, and the door sill pans. This is one thing you don't see much in residential construction. So what happens if you have a door that's not very well protected? Where does the water go? It hits the sill, right? If you look at how a door is built with the sill and the jambs, water just goes right through that. So especially in commercial construction, we would always do stainless steel sill pans. It's just a pan that has a little back dam on it that goes into the opening before the door is installed. And then we wrap the opening with our WRB and with building tapes, and all that goes down, and so all that water drains right into that sill pan and then drains out. So one of the things I like to try to tell my carpenters is, you want, before you go and put on that siding and flashing and everything, you want to think about, hey, can I blast this thing with a fire hose? Is water going to get in? Now obviously you need a door to create that seal, but just put an imaginary door there, and think that way. Think as if you were the water. Try to say, it's almost like a well-designed water management system is like building a boat, in a sense that it's designed to manage its water, and all of the cladding, the siding and everything that goes on top of that it's there as like a first line defense, no question about it. It handles the bulk water and everything so that the other systems beneath it don't have to work as hard, and maybe they don't have to be quite as robust in order to manage the water. Okay, so now we have this concept of a thermal boundary. So does anybody know what that means? Anybody heard that at all? So the thermal boundary, this guy Joe Stiebrick, he says buildings are environmental separators. They are intended to have us in an environment that's different from the outside. Understanding that basic concept helps understand what a thermal boundary is. So simply put, thermal boundary is insulation plus an air barrier. So insulation in and of itself isn't doing the job. The home needs to be, or should be, airtight, as airtight as we can make it. And the air barrier is a thing that does that. Insulation does not do that. Insulation does not stop air. Well, dense packed insulation slows air, but it doesn't stop it. So the other thing is they must be continuous and aligned to perform. So you don't want your airtight layer over here and your insulation here. You want them together. So these kind of these fundamental concepts of building science. Orange line is the thermal boundary. So it's one of the things we do is to define the thermal boundary. Joe defines, and then there's insulation. So Joe Stebrick, he's a really well-known building scientist. He's, I think he's done a lot for the industry. He's also really funny to listen to and very candid. He defines it as, calls it the fluffy stuff. Simple as that. He's candid. He's just, let's not mystify these things, But it could be any color, right? Doesn't matter. So in general, though, there are three main types of insulation. You have bats, blown in, and board insulation. So a lot of people ask this, well, how come these older homes weren't insulated? Does anybody know the answer to that? Yeah?
Cheaper to heat it,
Yeah. Yeah, that was a big reason. Big part of the reason, cheap energy. Other reasons? So it wasn't required for that reason until 1978. So we have millions of homes out there that were built uninsulated. Energy was cheap, as you mentioned. And the benefits of insulation weren't very well understood. Just nobody had it. Nobody cared. Turn up your furnace more if you're cold. And then there's a big focus on natural ventilation. So why would we seal our homes up? That's just going to cause problems. We like fresh air. Just turn the heat up. So they didn't have a lot of mechanical ventilation options and things like that. It was just open the windows. And also they weren't readily available. It's actually a little bit of a luxury to insulate, pre-1978. I've worked on some old homes and they were built in the 50s, and we found insulation in them and really nice homes. And so, so I think that they were installed as a kind of a luxury. And then there's this concept of the air barriers. We talked about the insulation, we talked a little bit about the air barrier, but what is the air barrier? It's kind of a mysterious thing. I remember when I first started learning about this stuff, I just didn't get it. So this says an air barrier system of materials designed to control the movement of the air into and out of the home, out of the building, plays a crucial role in maintaining energy efficiency, indoor air quality, and building durability. And here are a few characteristics and functions of an air barrier. Oh man, it's a lot of stuff. It does a lot, right? So I just kind of let's simplify that here. And I'm just going to say the air barrier is the tightest plane in a building's thermal boundary. Okay. So, and for best results, the air barrier should be continuous. So air infiltration is the #1 cause for heat loss. You can imagine that, all the leaks in a home, the heat's just finding its way out. It will find its way out. Because all you need is a pressure difference and an opportunity, and it will find its way out. Has anybody heard this before? Does my home need to breathe? Like, why would we seal it up? Why would we do all that stuff? It's got to breathe so it can dry out, right? Well, the answer is no. Homes don't need to breathe. We need to breathe. Okay. The homes, they need to dry out, right, if they get wet. And if they're getting wet, then we need to fix the problem. So this is a little magazine thing that I did back in 2011 called the Home Performance Journal. I actually printed out some copies if anybody wants to take one. It's sort of a funny little thing. And I did this, it's sort of a humorous thing, and I did this one segment here that says, you know, house allowed to breathe costs home owners money and comfort. Like, so it's a fun little magazine. So, home performance, combustion safety. So that's also a big thing. And we test the homes to make sure that they are not backdrafting. That's what this is. This is backdrafting. This diagram here is intended to show that how pressures work in a house. You can see that it's under negative pressure. That's why the walls are bowing in like this. Why is a home under negative pressure? Because of all the exhaust fans in the home, mostly. The dryer is an exhaust fan. And all these things, you get all these exhausts going on, it creates a negative pressure condition. And combustion appliances, some combustion appliances, what we call natural draft combustion appliances, don't like negative pressures. They require, it takes a very small negative pressure difference to actually backdraft a water heater, an old natural draft water heater. So you might look in your home and see if you have, you know, this kind of a water heater. And if you have a lot of rust, that's a sign that there's a problem. So, a deeper dive into home performance. Now, I create all these slides and probably don't have time for all of them. And if it's too much, just let me know, because I really kind of get into this stuff. And with my architecture background, I do a lot of detailing. And so I drew some details. But this shows like the vented attics in a half story, right? Insulating the half story. So this is the orange line is your thermal boundary. And then these